So let's move on then to the dot product of two vectors. Let's say I have two vectors like this, u and v, with the same length. If I want to define the product of these two vectors, it might seem natural to define that as a new vector with 3 elements, where I simply take the product of each element in the corresponding positions. So the product of these two would be, with such a definition, 3 minus 1 and 8. It turns out that this definition is actually not the most useful definition, and we'll come back to that when we look at the geometry. Instead, a much more useful definition is the following. I take the product of 3 and 1, then to that I add the product of the second element. So I add the product of 1 and minus 1. And finally, to that I add the product of the last two elements, 2 times 4. If I compute this, I get 10. Turns out that this number 10 is much more useful than this number where I simply multiply element by element. So we will actually define u times v like this. And to make clear that it's not the product element by element, we will actually call this the dot product instead of calling it the product. The word dot really comes from this dot in between u and v. Also, the convention is not to remove this dot, which we typically do when we multiply two numbers. There are a few cases where this thing is actually interesting, and it's typically called element by element multiplication of u and v. So we actually have two ways of defining what we mean by a product of two vectors. The way more common dot product, returning a scalar, and the element by element product, returning a vector of the same length. Because of this, we never speak of the product between two vectors, as such a statement might be ambiguous. We always use the words dot product or element by element product. The notation u dot v is not ambiguous. It always means the dot product. So we have the following. If I have two vectors u and v with the same number of elements, I define u dot v as the dot product of u and v. Don't call it just the product of u and v. And it's defined as a number. And it's defined as the following number. I calculate u1 times v1, then to that I add u2 times v2, and I keep on going until I reach the last elements. Using the summation sign, we can also write this as sum I goes from 1 to n ui times vi. And here is one more example. U is 2 minus 3 and v is minus 1 minus 2. The dot product between u and v will then be 4. If the vectors have unequal length, the dot product simply isn't defined. There are alternative names for dot product. It's also called scalar product. When you use the term scalar product, you have to distinguish it from the scalar multiplication. By scalar multiplication, we mean that we take a scalar and we multiply it by a vector or a matrix. In the terminology scalar product, scalar doesn't refer to me doing multiplication with a scalar. It refers to the result of u dot v being a scalar. And the dot product is also sometimes called the inner product. There's also an outer product, which we will look at later on. Let's look at how to do dot products in R. So here I have two vectors, x and y. They have the same length 5, so I can define dot product. Remember that you cannot use the multiplication sign in R to do dot product. In R, the multiplication sign is element by element. So if I do x times y and hit enter, I get a 5 vector where R does element by element multiplication of x and y. And that is not the dot product. That's not the scalar product because the scalar product must be a number. Instead, there are two ways you can do that. You can enclose the multiplication sign with two percentage signs. And that will give you the dot product, which should be 10 in this case. From the notation, you can see that it actually returns this number 10 as a 1 by 1 matrix. You can also use the definition of dot product, which says that you should sum xi times yi. If you look at the highlighted numbers here, you see that the first number is simply x1 times y1, while the second number minus 1 is x2 times y2, and so on. From the definition of the dot product, we see that all we have to do is to sum these numbers. So to do dot product in R, you can simply do sum x times y, and you get the same result, 10, but now as a single number, not as a 1 by 1 matrix. To summarize, you have two ways of doing the dot product in R. Using the first method, you get a 1 by 1 matrix. Using the second method, you get a number. We have some rules for the dot product. Algebraically, the dot product satisfies most but not all of the algebraic rules that you are used to from dealing with numbers. So in this slide, u, v, and w are arbitrary vectors, but they have the same length, so I can define dot product and addition between them, while alpha and beta are scalars, or numbers. The proofs of these results are given as exercises later on. First of all, scalar product are commutative. That is, if you do u dot v, you get the same number as if you do v dot u. You should really note that the equality sign in this case is an equality between two numbers because the dot product does return a number. After discussing the commutative law, we typically discuss the associative law, but there is no associative law for the dot product. For example, there is an associative law for numbers, which just says that if I want to add three numbers, a, b, and c, I can add them in any order that I like. The reason that there is no associative law for the dot product of vectors, well, it's simply because if I have three vectors, u, v, and w, u dot v dot w does not make sense. And since this does not make sense, asking whether it makes a difference if I start with u and v or if I start with v and w is a moot question. The reason this doesn't make sense is because the dot product does not return a vector. It returns a number. So once I've done a dot product of two vectors, let's say u and v, I don't have a vector but a number. Then I can't do the final dot product because the dot product requires two vectors on both sides. So dot products only of two, not three vectors. So instead we move on to the distributive law, and it turns out that scalar product is distributive over addition. So if I do u dot v plus w, that's the same thing as u dot v plus u dot w. Again, both sides are numbers. Try to prove this or look up the exercise later on and do a few examples in R to convince you that this is true. Because the dot product is commutative, I can also put the u after the parentheses and I get the same result. If I have one scalar product and one dot product, I do have associativity. So if I do alpha times u dot product with v, I can just as well do alpha times u dot v. For example, if alpha is 2 and I do first 2 times vector u and the dot product with the second vector v, I will get exactly the same result if I did first the dot product of u and v and secondly multiply that by 2. The third equality simply says that the same thing works if I have a scalar on v instead of on u. Again, try to prove this and check in R that it is correct. And the final rule tells us that if I have scalars multiplying both u and v like this, I can begin by multiplying the scalars and doing the dot product of u and v. The algebraic rules presented so far are exactly the same as the algebraic rules for numbers. And it might be tempting to think that anything you can do with numbers you can do with vectors. Turns out that that's actually not true, and we'll look at an example. And this is really why we need to go through all the algebraic rules that we have for numbers and check them one by one if they hold or if they don't hold for vectors. And later on we'll do the same thing for matrices. One important rule that we have for numbers is the following. Let's say that x, y, and z are 3 numbers. If I look at the equation xy is equal to xz, and let's say that I know that x is not the number 0. Well, in that case, I can divide both sides by x and conclude that y must be the number z. Y and z must represent the same number. That's an important result, sometimes called the cancellation result, that we can cancel the x's. Unfortunately, for vectors, this is not true. If I know that the dot product between u and v is equal to the dot product between u and w, then even if the u vector is not a vector with all zeros, I cannot conclude that v must then be equal to w. That simply isn't true. And here's an example. Let's say I have these 3 vectors, then you can easily check that u dot v is equal to 1, u dot w is equal to 1, so we have this equality. But as you can see, v is not equal to w. The cancellation law doesn't hold for dot products. You can't just simply cancel the u on both sides and say that v must be w. So keep this in mind. If u dot v is equal to u dot w, you cannot conclude that v must be equal to w. A result very similar to this is that if you have 2 numbers and you know that x times y is equal to 0, well, then you conclude that either x is 0 or y will be 0, or both. But it certainly cannot be the case that both x and y are different from 0. For the dot product, it's not true. You can have the dot product being equal to 0 and still have the case where neither u nor v is a 0 vector, that is a vector with all its elements equal to 0. For example, if u is 1, 0 and v is 0, 1, then you can easily check that u dot v is 0, but neither u nor v is the 0 vector.